dense computations. Most of the computations we care about here are sparse, and they are much more memory bound, right? And there is people realized that, and they made this high performance conjugate gradient benchmark, which is a much better measurement of how performant these computers actually are for the computations that we typically care about. And well, when we look at that, so this is a second ranked computer, which is pretty good at that, right? And this is Frontier, so the first ranked computer, which if you're using this for the sparse computations, then out of your exaflop, only about 1% remains. And so in high performance computers, so this is a well understood process. We called it the roofline model, looking at the green curve. Right? So if you have a lot of flops and not so much memory traffic, then you're getting essentially your peak performance. If you have to transform a lot from memory, then your performance, at least measured in flops, is actually going down. So the question is, are there maybe machines which are a little bit worse on the dense computations, but better on the sparse computations? And the good news is there is, right? Because right now AI is pouring money over computer architecture. And there are a lot of new devices coming up, right? So there are startups making these new devices and, well, trying to put them in the market. If you're wondering what this green thing is, this is the NVIDIA logo Toronto scale. They get, of course, most of the AI money, but that's a different story. So, and a computer or the device we're talking about right now is the GraphCore GC200 intelligence processing unit as in IPU. So this was made for, this was made for machine learning. And we actually have a bunch of these downstairs in the basement. And the way it looks like, so this has 1,472 small cores, and each small core has a bunch of 624K of SRAM, right? So this is basically like cache, but you're using it as memory, right? So this is essentially you're putting your data objects in there, right? Meaning you have limited memory, but it's very fast. And it has some nice other features. It has, I mean, it's mostly relying on MIMD, although it also has matrix units, as in same thing as tensor cores on the GPU, which are a little bit harder to use for scientific computing. Right? But it means that as long as our data is in this 624K on each chip, on each tile, right, we can access it very fast with very low latency, which is nice. And so the computation that we are looking at is essentially, well, this is a multi-domain simulation in cardiac electrophysiology, something that the cardiac modeling group here has been looking at for a long time. So we had a CPU-GPU code, which is extremely efficient at doing that. So essentially what you're doing, you're simulating the patient's hearts, reaction to stimulation, right? Trying to see whether you can actually induce arrhythmia in patients at risk. If you want to know more details about these computations, the people responsible are on the third floor. And yeah, so we call this code links, right? So this is what it computes. And well, we don't go too much into the details. The main thing is for the computation, right, that we can split it into a system of ODEs and the PDEs, right? And the PDEs, this is a fully explicit scheme. So essentially, we are performing a lot of SPMV, or sparse matrix vector computations for computing the PDEs, right? And the ODEs are essentially a bunch of flops, right? So they are not, I mean, it's not difficult to do that, right? It's just a lot of work. And typically, the time steps for the PDE are shorter. So in some cases, you may want to use multiple PDE steps per ODE step. And so what we're doing, right, we're performing a 1D partitioning here. So this is not a finite element technically, it's a finite volume scheme, right? So this means actually all of these pieces are relatively nicely behaved, meaning that the number of non-zeros per row is bounded. And that actually maps very nicely to an ELL-PAC type 1D partitioning, right, using traditional partitioners. And then these partitions are mapped onto the tiles of the machine. And well, we get some numbers on this. So ultimately, one of the problems is these machines, typically, since they were made for machine learning, they don't actually have 64-bit units, at least not so far. In this case, we could actually show with benchmarks that this is not a problem, right? So the results are still quite good. But yeah, so I mean, depending on how much you depend on very high accuracy, the current machines of this type may be a little bit tricky. But the main thing is we get actually quite decent speed on the PDE part, which is the more difficult part in a sense. But unfortunately, since most of the flops of this machine are locked away in these matrix units, we can't actually access them, right? And that actually means that on the ODE part, where we actually need a lot of these flops, the machine is not doing well, right? But this is depends a little bit on this design of the machine. This is not very general on these things. And if we are doing multi-stepping, as in, for example, if we are doing a lot of PDE steps per ODE step, right, then essentially everything that matters is the PDE time, right? And then we are getting a relatively nice speed up on this. And yeah, as I said before, so at least we are very certain that the GPU code on this is extremely good. So it's running basically pretty much as fast as the stream benchmark allows. And so this is basically running at what this roofline model or the memory bandwidth allows. We don't know whether the IPU code is as good as it can be, simply because the partitioners are not actually very good at partitioning things into many very small pieces and then actually filling these pieces optimally. So there are some things, but the main thing is, right, so this is something that we kind of, okay, so this was a test case, and this is basically showing, okay, yes, we can use these machines also for scientific computing. They're not only good for AI. There are some hiccups, right, but actually performing these sparse operations, they're actually very good at, because they're accessing so fast memory. Right? And essentially what we're doing, so this is a typical CPU GPU computation, right? So you have DRAM, you're fetching something from DRAM, you compute, then you go back to the DRAM, then you fetch more data. And essentially what we're aiming to do is something like that. So you try to load everything at once into SRAM, means you need a relatively large machine. But if you can do that, right, you can perform computations much faster. Right? And this is actually the CPU version of this Lynx code. Right? This is running on a Japanese machine, Oak Ridge CX. So this is a Cascade Lake. So it's a traditional Intel Xeon-based machine. And so here we are going from 4 to 256. So we are increasing the number of nodes by 64. And actually on the PDE part, we are getting a speed up of 128x. And so this is a super linear speed up, which happens because we have more cache. And so essentially what we are doing here is we are trying, so this effect has been well known in high performance computing, right? This just happens because you're doing strong scaling, right? So your problem gets smaller, you have more cache relevant to your problem size, you cache better. And we're trying to essentially exploit this effect, but do that systematically by loading everything that we need into cache. Right? And this would mean that, let's say, traditionally you would have, okay, multiple problems, right? You run them on multiple GPUs or something like that. Here, you would run everything on one big machine, right? But since they take they go a lot faster, you will still gain by doing this, right? Of course, this means we need relatively large machines, right? So as in machines which have a lot of this SRAM to be able to actually load meaningfully sized problems into them. And fortunately, these exist. So this is a Cerebras wafer scale engine. This is a machine made by a different company, Cerebras, in Silicon Valley. And yes, so this fork and knife, they're actually there for a reason. So it's a chip, it's a gigantic chip of approximately that size. Right? This is exactly the size that it can be made at with current technology. And it looks actually very similar. So it also has these kind of tiles which have memory and compute. The only difference to the IPU, or the meaningful difference to the IPU, is that they are in a 2D grid rather than in a 3D-like structure that connects everything. And so this means, so this is approximately 40 gigabyte of memory on there, so you can actually load meaningfully sized problems on this, right? And so the company itself, they have actually put out a bunch of papers showing very large speedups on problems that work well for them, right? Typically problems which have a 2D structure, right? Because you can imagine if you're mapping a 2D structure on this kind of communication, right, that tends to work very well. And so they claim 179x speed up over the frontier computer, which sounds suspicious, but looking a little bit at the numbers, and so this is something like a 4 GPU machine, which has something like 4 network cards, right? But then you need to talk to 4 neighbors. And if you're slicing this this large chip in a kind of a comparable size, right? So you're getting something like bandwidth differences of 100x and also similarly latency differences. So there are actually reasons to believe that the numbers they're quoting, of course, for specific type of problems that fits on this wafer scale engine and that maps well onto this 2D structure, that the speedups they're quoting are actually kind of believable. And so these machines, there are good reasons to use these machines, right? And so at EPCC, they have actually started to move PETSI onto this wafer scale engine. Right? And we are also planning, we are in contact with Cerebras to sort of work more in this regard. And what we saw in the last talk, right, moving stuff to the GPU, this will take a while before this can be done on these kind of machines. So it's really just in the very beginning stages. Right? But the hope is to accelerate computation. And there are also a lot of others, so including in addition to the Cerebras and the wafer scale engine, there are also some other companies making similar devices. And right now we are exploring a little bit which of these are useful for scientific computing, although our favorite is right now the wafer scale engine. Thanks.